So, so again, the webinar that you're on today is called Powered by Python, Expanding Functionality and Automating Advanced Workflows with Coreform Qubit's Python API. This is a workflow that webinar that we've looked forward to for some time. If you want to go ahead and advance the slide, Greg. So as I mentioned, I'm Matt Cederberg, a co-founder and CEO at Coreform. Greg Vernon is Director of Product Management at Coreform and a longtime Qubit user. And so today he'll be leading us through this webinar about automating workflows with the Coreform Qubit Python API. So this webinar will be recorded, and throughout the webinar, as you have questions, go ahead and just type them in the Q&A, and either some of us will answer them on the back channel, or we'll interrupt Greg if it makes sense, or we can answer them at the end. Again, this webinar is being recorded and will be posted on YouTube. So we're going to start off the webinar by just understanding a little bit of who's here at the webinar, to give Greg a little bit of a context to see who he's talking to. So the poll that we'd like to invite you to fill out is, how do you usually use Qubit? And you can either let us know that maybe you don't currently use Qubit, if you mainly use the Qubit GUI to get your work done, if you use journal files as well, or if you are already using Python scripting. So let's leave this poll open for another 5 seconds. Go ahead and close it out. Okay, so here's the results of who we've got on the webinar today. So it looks like the majority of those on the webinar are using the Qubit GUI, with a sizable number also using journal files and Python scripting. So hopefully this is a helpful webinar for each of you to increase in your usage of Qubit tools. So with that, let me turn the time over to Greg.
Great, thanks. Can we get rid of the poll thing? I don't know if I can close that, or if I should or shouldn't.
Okay, is that good?
Yeah, I think so.
Okay.
All right. Yeah, so thanks, Matt, for kind of introduction, and I'm pleased to see so many people on the webinar today. I'm excited to learn about Python and Qubit. So from a topic standpoint, this is going to kind of dictate how we're going to go through this. I'd like to just go through just navigating Python within Qubit for any new users on today's webinar, or that might be watching this after it's uploaded to YouTube. There's some basic things that you might be familiar with if you're familiar with Python, that you might be interested to start using in Qubit. And then I'll give you kind of a quick run through of some of like the workhorse functions. They're the things that I use 90% of the time to do most of my work. And then I'll kind of go off maybe to grab a few functions here or there that maybe fit in. But really there's only a few functions you really need to start getting a lot of power and use out of Qubit's Python API. And then I'll start talking a little bit about some of the advanced Qubit Python workflows that you can build that can automate. What I'll show is an entire simulation pipeline in the open source Moose application even. And I personally just really like examples, and I like just walking through things. So this is going to be example based. So I'll show a few applications to showing how you can write your own custom mesh sizing using Python, as well as writing a custom mesh importer. So it's often a request we get a lot, is people want to have a mesh format from some other code that they're using, and they want to be able to import that and operate that within Moose, or within Qubit, or maybe they've written an in-house code with their own format, and they want to expand out to using Qubit. And then I'm going to show part of this advanced workflow of complete automating a simulation. We'll generate some Indian standard beams, and then we'll add this workflow not just as a script that can be run, but it will actually add it into the Qubit GUI for reuse, and you can distribute it to other folks in your departments. And then I'll show how to actually combine that together to then automate an entire Moose simulation workflow, from pre-processing in Qubit to running it in Moose, and then extracting out data that you want from your simulations. And so kind of why Python, right? So we saw a lot of people are using journal files. Journal files actually run what's called the Qubit command language. And so if you're familiar with the GUI, you might even be typing in some commands like reset and brick X1. Those are all Qubit command language. And most professional Qubit users do use, I'll call it CCL, to automate their workflows. But we see that Python is primarily then used by power users. And power users will use Python for improved reusability of the functions that they're writing so they can distribute it to the other folks in their department. But also it kind of expands what you can do because CCL doesn't really support these sophisticated data types that Python provides, like lists and dictionaries and different objects and object-oriented programming. As well as you go off to maybe something like the pandas module or NumPy and SciPy. You have all these different functions that you can now access. And what you'll hopefully see today is that it's easy to adapt. If you have Python experience, it's easy to adapt that to Qubit. And even if you don't know Python and you know CCL or you can have some experience with Qubit, you can then easily kind of ease into learning how to use Python. And so, yeah, it really is a pretty gentle learning curve. And what I'll show today is this workflow of using the GUI to generate CCL and then translate that into Qubit Python. And so what I hope you get out from this today, I'm going to focus on breadth as opposed to depth, just to show you what some of the things are that you can do. And so hopefully you'll be able to start using Python to accelerate your workflows, and then you'll be aware of some of the more advanced functionalities. And then we encourage you to give us your feedback on maybe specific deep dives you'd like to see in future webinars. And we intend to do some more maybe deeper dives into how to use Python for specific outcomes. So the first portion of this presentation or of this webinar is getting started. So there's 4 things I'm going to just try to show you. I'm going to show you how you might add modules to Core4m Qubit's Python environment. So if you want NumPy or SciPy or Pandas, scikit-learn, other things, how you go about doing that, as well as how to actually execute Python from within the Core4m Qubit GUI. And so there's maybe some settings that you need that for now you'll need to set. And then how to access our documentation, and then how to then use this workflow of using the GUI to generate these Qubit commands. So the first of these topics was just how do we add a module to Qubit? So if you're a Python user, you might be familiar with the pip module to install custom modules or whatever modules you want into your Python distribution. But what you're going to do is you're going to run the package Python. So we package Python within, I'll just pause this here, within your installation directory, bin, and then there's a Python 2 and a Python 3 directory. So with whichever Python you choose to use, we will be deprecating Python 2 in the future as it's now end of life, but we still do package it. But we do encourage you to move to Python 3. And then you're going to essentially run Python, tell it to run the module pip with the install flag, and then you would write down in a list your modules. So in this case, I've chosen to install, oops, play this again. As you can see, I've chosen to install NumPy, SciPy, and SymPy into my user directory. You can choose to install this directly in the install directory if you want, not as a user, but then you would need to run this as an admin and without the user flag.
Greg, can you confirm, does that work on Linux as well as Windows?
Yes, that should work. The directories will be different. This should work on Linux as well. Yep. I don't believe that there are. I do most of my Qubit work in Windows. I believe that this Python syntax is equivalent across all platforms, but there may be. I mean, the Python execution might be tailored to Linux, but I think this is the same command syntax. But obviously you'll find a different installation directory. That's a good question. Yep.
Thanks.
All right, so before we move on to, oh yeah, so next I wanted to show just so the complete getting started. What I'm gonna do is I'm gonna open up Qubit as it's installed on my system. And okay, Zoom is always in the way. So let's maybe move Zoom somewhere else. So when you open up Qubit, a couple of things you'll notice is that there's a command line that should have just a few tabs. And what we'll need to do is in Tools, Options, under Layout, there are options to add the show the script tab. So you can see just as soon as I click this button, the Show Script tab pops open. And you might also want this command shortcut, especially if you're new to Qubit Python. As well as under General, we can set our Python version to say 3. And then we will save this, and then we'll reboot Qubit so that it's actually loaded up the Python 3 runtime. So now if we look at our command line, we have both our Qubit command language tab as well as our scripting tab for Python. And so now what I want to show is how would we execute Python from within Qubit? Well, so I'm in a Python session here, and I can do things like print 2 + 2 if I chose, and I can get out 4. I can do things like import NumPy, and maybe say that a equals numpy.zeros, shape equals maybe just a 3x3 matrix, and I can print A. So this scripting tab is now a Python interface inside of Qubit. What you might want to see also is the actual documentation for Qubit. So I'm going to use the documentation quite often today. If you go to our website, under Core4m Qubit documentation, there's the online help. And this online help, this same structure exists in the packaged Python or the packaged Qubit help as well. But you'll go to the appendix and then Python. And so if we then click on, say, the Python interface, we'll see that there are classes. We'll talk through some of these classes today, but also then all of the functions are really within Qubit interface. We'll talk later about some of the advanced functionality about how to use Qubit or how to call Qubit from a separate Python, like external script. And if you ever forget how to do that, there's documentation here for how to import Qubit into Python. And we'll talk about this a little bit more later. If we just look at the Qubit interface documentation, we can then see a listing of all the functions that are accessible. And if we say click on one of these functions, it'll take us down to documentation further down the script. It provides information about what parameters you need to pass in, as well as what things are returned from the functions. So we'll use this today as we walk through this webinar. So now what I want to show is how you would use the Qubit GUI to generate functions that you might use in Qubit. So it looks like most people are familiar with journaling, but if you're not familiar, Qubit, before it was a GUI, was actually all Qubit command language. And commands are then journaled or logged into a history file. And so what we'll see is that as we start doing things in our in the GUI, so maybe I'll create a brick of dimension maybe 10, 5, and 1. The GUI actually sends the command to the Qubit command language processor. And then this is journaled in our history. And so what I could do is I can do things like, well, maybe I should just use the GUI for a little bit. So I clicked on like new file, and that created, that sent a command like reset. And so I can do things again in here like brick x10 y5 z1. and do things that I had previously done inside the GUI. So many of you might be familiar with using the GUI to create these syntaxes and then copying your history file and putting them into a journal. These are also, though, we also log these to the scripting panel. So you can either grab maybe like the entire qubit.cmd, or as we'll talk about, this is the first workhorse function, is this module cmd or command. So every single qubit command can actually be sent through the qubit Python interface and executed as if you had entered it into the command editor. So as you can see, I can do things in here like qubit.cmd and pass in a string called reset. And that is effectively the exact same as running reset from within the qubit command language. And I could then do qubit.cmd brick x10 y5 z1. And then I can create this brick. Now, if you're a Python user, right, you might want to be able to like pass in some arguments into your script and then run those. So again, many of you might be familiar with APRI-Pro within the qubit command language. It will create like APRI-Pro variables. But the Pythonic way with a string is to use string formatting. And so just as an example, say that we have variables called maybe x, y, and z. Oops. And we want to then pass these into our function. So the Pythonic way, maybe I've got some, so my string. So I might copy this overall string, and then Python formatting, you replace things that you, the constants that you want to replace with something with curly brackets, and then you use the string method of format. And then format takes either positional or name value pairs. So in this case, I'm just going to enter in I'm going to pass an x, y, and z into the string. And if I print now my string, we'll see that it's been replaced with these values. And if I change out the order, maybe I turn it to like y, x, z, we'll see that then they've changed again. So string formatting is the recommended way to then take your variables that you've calculated in Python and put them into your strings. And you pass this string into CMD. And so putting it all together, your command might look something like this: qubit.cmd. Let's begin our string. I always like to kind of begin with my kind of outline. I'm going to put in brick x, curly bracket, y, curly bracket, z, curly bracket, and then format with x, y, and z. And maybe I'll qubit.reset so we can see this again. So if I run this again, we'll see that this has created the string, entered in my values, and then executed this command. So that's the qubit CMD function. Something that for new users you might like to see. You can't use string formatting here, but if you're not exactly sure, or you just want to do something quick, you can type commands into this little shortcut tab, which is one of the options that we'd set previously, and then it'll just run these. And so that can be useful for when you just want to say, I've got some command and I just want to see it run real quick and maybe extract out something. So I personally don't use this a lot, but it is a good kind of training wheel. Another really useful command, let me open up a good file for this, is a method called parse from qubit list. So I'm actually going to find this in here. Or parse qubit list, here we go. So parse qubit list will take the qubit command called list, and it'll extract out key information into maybe an array that you can then use in qubit. So let me just demonstrate this. So you might be familiar with doing things like, say, list and then maybe totals to say maybe get out maybe the total amount of volumes or surfaces in a model. You might also say list volume with X chord greater than 0. And then it prints out, so body 14, body 13, 12. So it's telling us what volumes have their x, or the x value of their centroid, or their center, is greater than 0, and just lists these out. Now, this maybe is not as useful as you might hope, because we have to come through and copy body 3 and body 4. But in Qubit, the same syntax, qubit.parse qubit list. The first argument is what we had typed in, is going to be volume. So what do I want out? I want volumes. So that's the first argument we're going to pass in as a string. The second argument is the logic behind it. So with x chord greater than 0, in this case, again, as a string. And again, I might use string formatting if I wanted to change this value of 0, or maybe I don't know if it's going to be x chord or y chord or z chord, so I can do string formatting for all of these. And if I wrap this in a print statement, we'll see that now it's giving me out a tuple that has all of the volumes that meet this criteria. And I could do more things. I could say maybe I want to know the vertices in volume 1. And I could print out those vertices. I can go the other way around. Maybe I know a vertex and I want to know the volume. So I could say volume in vertex 1. Right? This is like vertex maybe 20. Volume 3 contains vertex 20. So you'll really find that this parse qubit list is a really good way to get out key information, whether it's I want to know maybe what elements are in a certain volume, or what volume contains a certain element or node, or getting out geometric properties and doing a lot of quick calculations. So this parse qubit list is one that I highly recommend. It's one that I use all the time. A few other options I'll just go over kind of briefly is that there are there's, as you're building models, you might be getting out like, I want to know what my most recent volume ID is, so that as I create another volume, I know what that new ID is. So there's a command called get last ID, which accepts a string, and you can tell it that the string is the geometric entity. So maybe I want the last volume that was created. Again, I'll wrap this in a print statement. It tells it 14 was the last volume. So if I go in and I create a new volume, maybe sphere radius 0.2, then that was volume 15, because it was incremented by 1 from the previous last ID. And so again, I can reprint this again, and it'll tell me that 15 was the last volume that I created. And that can be really useful as you're building scripts that may not be building in a pristine qubit session. You might be building inside of an assembly. You need to know what the last vertex, curve, and volume IDs were. And lastly, there's also get entities. And so this is useful if you want to know, I need to have a list of all of the volume IDs so that I can loop through them, say. So let's wrap this in a print, qubit.get entities. And again, here we just tell it a string of what kind of geometric entity we want to have. So in this case, I want a list of all my volumes, or maybe of all of my vertices. So if I maybe delete a volume, so maybe I'll delete, this is volume 9. I can then print out again this get entities volume, and you'll see that 9 is now missing. So those kind of 4 commands form the basis of a lot of the things you'll do. One of the things that I'll also mention is that we also provide a list of these entities, so like volumes and bodies. So bodies, volumes, surfaces, curves, and vertices, and they themselves have their own functions. So for like a surface, I can actually query the ASYS geometry engine and get out things like the principal curvatures of a surface, or get the normal at a certain location. So say maybe I want to know like a tangent along some location of this curve 190. So this would be qubit.curve 190 is how I access that curve. Maybe I'll put this into a variable called C. And then I can do things from its from the object. I can get a position from its U value. So U being the parameter along its length. So maybe like at its midpoint. And I'll wrap this again in a print statement so I can get out a tuple of its XYZ coordinates. I can then pass that directly into curve tangent. So now curve tangent will give me the tangent at this location. I can get out the tangent value. And so again, that's another, these objects of curve, volume, vertex, and body have a lot of really useful functionalities in them that you should take a look at if you're interested. So those are the workforce functions.
Great. Can I ask you a couple questions before you move on?
Sure.
Yes. Here's a question. How do the coordinate axes appear alongside the volumes?
Yeah, good question.
Setting or?
Yep. So that's a little GUI icon up here. So it's toggle scale. So it's right next to where you can toggle the perspective from parallel or perspective. And this is one that has like these little tick mark axis grids. And so if I turn these on or off, they'll pop in and out. Very good question.
Great, thanks.
Yep.
Here's another question.
Uh-huh.
Is it possible to define as Python interpreter for qubit the Anaconda distribution?
That I don't know. I know that you could use, so we'll show this later, you can use whatever external Python you want, as long as, I think you have to make sure that the versions match what qubit's version is. I think that's a requirement. But if you had your own external Anaconda distribution, you can then call qubit from that Python, but you wouldn't have the GUI attached with it. And we'll show an example of that later today.
Okay. Thank you.
Yeah. All right, so moving on. So some of the advanced functionality. So what I want to show first is, so I'll kind of move back and forth. I want to show a real problem that came courtesy of Professor Thomas Roth at Purdue University, who had a question regarding how to mesh a model or a geometry for his computational quantum electromagnetics calculations. So let me just open up, just open this up real quick. So this is just and so if Professor Roth is on, he may be able to correct me if I get these wrong, but this is just a surface model. So he's just doing some kind of maybe a boundary element type approach. He's not building a tetrahedral mesh, but he does need high quality triangles on his mesh. And as you can see, some of these triangles are just from the default meshing schemes and meshing sizings. Some of these are not very high quality triangles. But he also wants to reduce the number of triangles over the entire domain. As you can see, even VTK is having a hard time rendering because this model is actually a very, very thin volume. And so if we zoom in, we can kind of see that here's like this edge. So this is a very highly disparate scale. If we turn off the meshes, you can see he's got some surfaces defined. And what we'd like to do is we'd like to go through programmatically and find small surfaces and assign small surfaces with small meshes, and then larger surfaces with larger meshes, and then let the qubit meshing algorithm blend between those two meshes. So let me go ahead and I'll mention a couple of things also. So the original journal file, if we look through, so this is using just standard qubit command language in journaling. Again, using this APRI-Pro style syntax. As you can see, we're not in this case using looping. We're trying to track what our volume IDs might be, and like what surface IDs are. And this, if many of you might be familiar, this can sometimes be brittle. that an ID might change if you change something upstream. So I've actually rewritten that creation into a Python script that uses, again, string formatting and the commands like the get last ID, so that I don't anywhere have to actually worry about what the specific ID is. I just have to worry about relative IDs. So as long as I track what as long as I know how many vertices are being created by each command, then I can do things like offset or index to them. And then this actually turns out to be only about 160 lines compared to almost 500 or so lines with the standard journaling. But then, so for the meshing though, what I've done is, we'll just walk through this just briefly, is that I'm actually getting a list of all the surfaces, and I'm I'm starting off a list of the surface areas. For each surface, I'm going through and I'm actually computing the surface's area, and then I'm turning this new list into a NumPy array. Now, once I have it in a NumPy array, what I'd like to do is that there's a command, or there are options in Qubit under meshing for intervals. There's this automatic sizing from fine to coarse, and there are 10 increments here. So if I zoom down to maybe say this surface, I could say that this surface I want to be meshed with as coarse as possible. Oops, I gotta turn on. So let's do delete mesh. So this is a very coarse mesh, and as you can see, maybe there's triangles that are already not very good. Or I can set it to maybe a finer mesh. This should work anyways. Maybe as fine as Qubit decides it needs to do. Well, yeah, and so the issue here is that so I can assign a size, but it doesn't really Qubit doesn't see a need to make this any finer because there's no neighboring triangles. So what I need to do is I need to mesh from the smallest surface up to the largest surface, so I can dictate element sizing. So what I've done, so first I'm just getting the log 10 of these surface areas, and I'm putting them into a histogram with 10 bins. And so I've sorted these areas into those bins, and I'm going to mesh them from smallest to largest. And so if we run this script, you can see this as it's being generated, we can actually see the mesh being calculated. And so we can see that this has now worked to mesh the smallest surfaces first, and then gradually transition to a coarser mesh. And so this is then the kind of quality triangle mesh that Professor Roth is looking for, but then also does grow to large elements, so we don't have just a massive amount of degrees of freedom. And these elements are quality enough for Professor Roth's codes. So this is an example of where I've taken existing functionality within Qubit, it's automatic sizing, and I've added my own little flavor to how to actually mesh this particular geometry by sorting surfaces from smallest to largest, and then assigning them to the different auto factors through binning. So another example that I want to show, the next example I want to show is writing a custom mesh import function. So let me just.
Hey, Greg, before you
Sure.
move on, there's a question if this script that you used would be made available to attendees.
Yeah, what I was planning to do is upload these to Zenodo, and then we'll upload this YouTube video to YouTube, this webinar to YouTube, and then in the description of that video, I'll put in a link to the Zenodo with these scripts. Yep.
Great, thank you.
The one exception I might just check with I'm fine to provide this script, the generation script of the geometry for Professor Roth. I'll have to ask him for permission first before I distribute that script itself. But certainly at least the meshing script is fine for me to distribute. And the other ones I'll distribute as well. as possible. So good question. Thank you. So the other example I wanted to show, yeah, so a mesh import. So you might have seen in the Python interface, there is a class for mesh import, and there are some functions in here. I'm not going to go through all of these functions, but just some of the basics. So we recently had a request come in from someone who wanted a Gmesh importer. And so Qubit does not currently support Gmesh, something that we'll certainly look to add, but you might have similar situations where you might have some other mesh format that you want to add, and we just don't support it yet. And so in this case, I'll just show, I've got a Gmesh file of a mesh sphere with tetrahedra, and I've written a Python function that will actually go through and parse this file and then use the Qubit mesh import function. So I'll run this first, and then I'll talk about just a few, make sure that you have these correct as you run through. But what this does is, as you can see, it imports this mesh, and I have now a mesh-based geometry for this model. So I can do stuff like continue to add side sets and do partitioning if I want to, although it is a facet-based geometry. Now, the key part here is that so as you're adding elements to this mesh import object, it's critical that at the end that you do convert it to a mesh-based geometry. So this Qubit this create mesh geometry tet all. So I happen to know I don't have any logic in here to look for hexes or any other kind of elements. I just knew these are all tets. And then you need to delete this object after you've run this command. If you don't delete this object, the next time that you try to import another mesh, you'll crash Qubit. Because really, the Qubit Python API is really just wrapping C++. And so we're having to delete out, clear the memory of the previous mesh import. So these two lines here are critical once you've finished your import. But so then you could adapt this to, if you have your own custom code or your own custom mesh that you've written maybe in your lab, you could then adapt Qubit to be able to import that. Now, the last example I want to show is to build up this Indian beam standard and then work all the way through the Qubit GUI and running a Moose simulation. So first, I'm just going to go ahead, I'm just going to open up a new Qubit here. And if you're not familiar with Indian standards, you're probably familiar at least with, there are US standards for beams. And so it's no surprise that there are Indian standards as well. And so what I've done is I've just gone through and I found one of these, I think it was, section 3 beam, and they've got definitions for how to make these geometries. And so what I've done is, let me close these. Is I've written a Python module that has, again, many different functions. So in Python, it's recommended that, right, as opposed to writing like a long script, try to functionalize things, turn things that you're doing over and over into a function that you can then reuse. And so I've written a little class here that defines section 3 parameters, like the dimensions, as well as a few things like to validate that maybe that a designation that someone has entered is valid. And then I've got these different functions that go through that build geometry, and actually goes all the way through building and exporting mesh. And then the way that I've handled the geometry, this is, again, Qubit doesn't have yet a sketcher. So what I've done is I've done the geometry calculations, and then I'm actually using SymPy, so symbolic Python, to actually solve a few equations that I need to do to enforce constraints like tangencies and things. And I've calculated these equations by looking at the drawing and then building up a system just geometrically. A sketcher is definitely something that we're looking to add to Qubit sometime in the future, but it isn't there today. But this is just one way of where I've been able to use the Python interface or the Python environment to be able to solve a problem for myself. And so if I just there's a couple ways you can do this. Is that I can either copy paste this into the script tab, but we also have the journal editor, and within the journal editor you can be either editing a Qubit command language file or a Python. And so if you want to swap between, you can actually click these here. But what I'm gonna do is I'm gonna open up actually this Python script. And then I can just run it from within here. So we'll just watch as this function goes through. So now it's meshing, and then it's exported out to the Exodus file. And so that's now something that, right, I've automated this away if I want to. That's just an example of, again, some of the things that you can do by using Python. There's no way that I know of without doing I mean, you have to solve these equations by hand manually and then enter them in. There's just no clean way to do this, in my opinion, with the Qubit command language. But because Qubit Python subsumes Qubit command language, is just a part of it, and then provides you all of the power of Python, like this is the way to build complex models like this in Qubit. So then what I wanted to do is maybe I've decided that, you know what, I'm doing a ton of work, my department's doing a ton of work with beams. And so I need a fast way to just be able to load in any beam that I want. So we provide a way for you to actually add functionality into the GUI as a GUI-based command. And so there's the ability to add a custom panel. And what you'll do is, we have documentation for this, which if I can find this quickly, I think it's under customizing user experience, adding command panels to the GUI. There's documentation here. And what you can do is, there's the open source Qt designer, which you can use to help build, or which you'll use to build the actual interface within Qubit, wherever Qubit is. So what we'll see is if I, let me see if I can import or open this up from a recent. So I built a little panel UI here that just asks for section designation and a link. And then I've done a few more things with XMLs that are, again, these are documented in the documentation, but I've then adapted my original script to an apply script with a few extra things. So I happen to, you know, import user panel from the Qubit GUI. So there's a few extra things I've had to add. Yeah. So there's only a few things that change. So once you've written that first module, it's actually really simple to move forward. What we can see now is that I've got this under create geometry volumes. I've now got a GUI command in here for Indian standard beam. And so I can create an SC100, maybe of length 1,000. And maybe I want to also add like maybe an HB150, also of length 1,000. And I can just choose any of these and just go through and add beams to my heart's desire. And again, the way that I've managed to do this is because I can do things like define an object or a class in Qubit. I've got all of these dimensions just pre-stored. So that's a really cool thing you can do with Qubit, with the Qubit GUI. And you can do this for volumes, or you could add the meshing scheme that we talked about previously. You could add that as a sizing scheme if you wanted. And you could add arguments, maybe for like how many bins you want to have, or do you want log scaling or linear scalings. So yeah, all of these functionalities you can edit by using Python as like the backend for it. So then the last thing I want to show for you today is how would we now maybe automate our entire simulation process. And I'm going to show this in Moose. If you're not familiar with Moose, it's an open source file element code. It's managed and maintained by Idaho National Laboratories, but there are many users across the world of Moose. Moose it's based on the Exodus mesh format. The Exodus mesh format is its preferred mesh format, which happens to also be the native format from Qubit. So a lot of the Department of Energy codes are based on Exodus and then have used Qubit over the years as their preprocessors. They have a great getting started. If you're interested in get started with Moose, Zoom is in the way, so I can't see. And so they have one of probably the best documentation I've seen for how to actually get started with installing Moose if you want, and even for Windows, using Windows Subsystem Linux, which is actually what I'm going to be using. So I'm just going to open up my Windows Subsystem Linux, and I'm going to activate my Moose Conda. I'm going to go to, I built a Moose application called Struct Mech, and I've got my little beam problem in here. So if we now look at, so I've written a little script here called run beam moose. This is also on my Windows Subsystem Linux. And I'm doing a couple things here. I'm going to actually import this module that I've written previously. So I'm going to import that module so I have access to building those beams. I'm also going to import, so I've also built the CCAS library, which is another open source tool. It's the Sandia Engineering Analysis Code Access System, which is what Exodus format is a part of. I'm going to actually import a module there called exodus.py or exodus.py. And there's documentation on the CCAS GitHub for this Exodus Python module, which actually lets me go in and query Exodus. So I've just written a very simple function that's just going to, within a certain directory structure that I've built, I'm just going to do a little bit of file management of moving. Well, I'm going to first try to build, I'm going to build my geometry, and I'm going to then do some organization. I'm going to move my input mesh into a directory called syminput. I'm going to run moves and move files to the output. I've also structured this param input file with a kind of APRI-Pro-like syntax where I'm going to find and replace certain strings in my input file with the mesh format that I'm exporting. And then I'll actually submit this Moose job through the subprocess module. So with a subprocess.call. If you're using a high performance computer, you might have a job scheduler like Slurm. And there's a Slurm Python module that you might use in that case. But as you can see, I'm going to be able to pass my MPI command. And then after each one finishes, what I want to maybe post-process is I want to figure out the max von Mises stress. And that's where I'm using this Exodus Python module to go in, extract out the von Mises value at the last time step, and then write out that maximum value to this file. So let me just go ahead and I'm just going to use my system Python here, which is that in the Conda environment for Moose, this is a Conda Python. So it's packaged by Conda Forge. And I'm just going to just straight up copy paste, this script into here. So you can see it's checking out license for Qubit and running Qubit. And so it's initialized. I should talk about that, by the way, that one of the important things is after you've imported Qubit, so this is just now off and running, and you saw I just flew through the Moose simulation right here, is that after you import Qubit, you need to, so I'm down, where's my, oh, right, because it's in, So one of the things that's important is that when you import Qubit as a module, is that you initialize the Qubit session with this .init, and then you pass it an array of the options that you want. And so you can add things here. So maybe you don't want journals, or you don't want the banner that showed up at the very beginning. If we look at our Qubit documentation, again, for Python, you'll see that it talks about this. You zoom in here. So qubit.init, so in this case, I'm telling it, okay, so if I'm giving it any commands, I tell it Qubit, and I don't want a journal, so no journal. And I could add more options here, maybe like no echo. And you can get out what those environment commands are that you can pass in through controlling the session under execution context. So here's what this no journal is, no echo. You can turn warnings off, information off if you want. Some of these you can't do, so you can't do things like display, like a display, but most of these are pretty self-evident which ones you can and can't use. But if in doubt, just test them out and see which ones work and which ones don't. So now this is off and running, my little design experience. So I wanted to run through maybe all of those beams for a certain pressure load and get out the maximum von Mises stress. Maybe find which of these beams has the least or the lowest von Mises stress value. And so I can just demonstrate that if I go to struct mech, problems beam, and then I think is it sim output. Yep, so I have this sim output, and I can take a look at this CSV file. Oh, I didn't put I guess I didn't put my end line commands here. And I probably pulling from like the wrong time. But this is just the example of being able to use CubePython to not just build a Python script, but also submit it and even do post-processing if you want to. And so this is a Friday at 5 p.m. I could go home and come back on Monday morning with my entire simulation having completed. So as you can see now, my execution has actually completed here. So I've actually went through all of those examples. So yeah, so those are all of the examples I wanted to get through today. I know we're just about out of time here. But yeah, I wanted to just, I can't stress this enough, but we see you'll get a lot of errors, or you'll see errors about couldn't initialize and just seg faults with importing qubit from external qubit, unless you run this qubit.init. So if you've done import qubit and you've tried to run a qubit command and you get an error, it's almost certainly because you forgot to do qubit.init. And so I encourage you to ingrain that in your memory. Again, I want to give a special thanks to Professor Thomas Roth from Purdue for letting me demonstrate Python on his example. And I recommend that you go to his website. Looks like he's doing a lot of really cool things. And that's all that I have for today.
Great.
So
Thank you. Yeah, great. Thank you for the excellent content. We'd like to close with one more poll, and then we have a few minutes for questions. So we're just doing a check on seeing how well we did on the learning objectives. So if you wouldn't mind filling out these two questions. One, after what you saw and learned today from Greg's webinar, do you feel comfortable to begin using Python in your qubit workflow? And then a kind of a related question, would you like to see another webinar about using Python in Coreform Qubit? So if you just, I'll just leave it open for another few seconds. We see this feedback that can help us as we plan future webinars. Okay.
And I thank you for your honesty. For the people who said no and undecided, I would love it if you could provide us with some feedback about how could we make you feel more comfortable with using Python. Is it a matter of improved documentation? Is it more webinars? Do you have other questions maybe that we weren't clear on? I really would appreciate your feedback on that. If you could send us an email to support@coreform.com with what you think we could do to help you feel more comfortable using Python. I would really appreciate that.
Yeah. In addition, we had some requests during the webinar for where they can add feature requests. The place to go for that is our forum.coreform.com. And also those of you that have asked for another webinar about Python and Coreform Qubit, if you have any specific questions, that could be a place to drop those as well.
So this is our forum. So for those who asked, forum.coreform.com, and you can ask your questions in here. And yeah.
Great. So we have just, again, a couple minutes for questions. We have a few more coming in. Greg from AIDA using the API, is it possible to determine if hex mesh elements that belong to two different blocks share a face?
Yes, you can. So there is it's uh, so off the top of my head, um, the one way you can do this is we have let me just zoom this back out. Um, so there's probably an easy way to do this, but there's also the way that might be a bit more intense. But what you can do is there's under mesh query support, you can either you can get connectivity. Whoops, here we go. So you can get connectivity for certain elements, and then you could get their sub elements like their faces, and you could look for, um, is this, are these nodes shared on different faces? But you can also like get the geometry owner, and this will give out multiple. So let me just see if this will work here. Let me just reset brick x1 and 1 again. Let's move vol 2 by x1. And so if we do imprint all, merge all, mesh vol all. So this is what I think you could do is, you should be able to, let's see if we can find draw hex all. So if we could get out a face on the interior, so let's go with like so let's say we know what our nodes are here. So like 595, 596. So what we should be able to do, hopefully this will work, do it live. In the scripting tab, qubit.get geometry owner. And it's going to take in, so node, and then the number, so 595. And if we print, so this is told us surface 6. And then so surface 6 is probably a merged surface. So we can do qubit.is merged surface 6. And so that's telling us that, yep, so this surface 6 was a surface that we had merged together with another surface. And so it's actually two surfaces kind of in one. And that this node has been on that surface. And so it's maybe like a two-step process that you might do there. But that's how you would determine, and these nodes then define like the face of that element. So yeah.
Great, thanks.
And you could obviously from those nodes you get out what element they were. Yeah. So
okay, just a couple more questions. From Jonathan, will we ever see Python qubit on PyPy?
That's a good question. So to be quite honest, I just don't know enough about that. But my guess would be no, partially because the Qubit Python API does wrap some of like the ACES geometry kernel, which is a proprietary kernel from Dassault. And so we've had this discussion before about how could we make Qubit maybe more open. And it really comes down to that a lot of the power of Qubit comes from a lot of our the commercial libraries that we use, and so that can be difficult. However, we do offer a free version of Core from Qubit, which you can request from our website. It's called Core from Qubit Learn, and it's a fully functional Core from Qubit, with the only limitation of you're limited to 50,000 elements on export through our built-in exporters. So these built-in exporters with Qubit Learn are limited to 50,000 elements. However, in a pinch, because we provide Python, right? You could obviously, if you had your own custom format that you needed, you could write that out. But it is a non-commercial version of Qubit.
Great.
But yeah, that's at least one way that you can at least get that access if you want to.
Okay. All right, and then last question from Duke. Can I get an example code mesh that uses Python to mesh a model, like a shell or a solid? And I wonder, there's a lot of big questions coming in, Greg, just acknowledging the value in having access to these scripts that you've been writing and maybe others. So I think that's something that we can share out after the webinar.
Yeah, and Ada has a good question too on the parse qubit list. But yeah, it does also handle elements as well, I believe. So we could say node in hex 1 and print this out. So yeah, it essentially it will do anything that you can do from standard qubit list. So if you could list node in volume, and this is usually how I build my commands, is I first I try to think here, like list node in hex 1, and I see if it gives me out any input, then I know it's going to work. So that's typically how I'll then capture this and put this into my qubit command for it. So yeah, that's a good question.
Great. Okay. Well, again, thank you so much, everyone, for attending, taking an hour today to learn with us. Greg, thank you so much for your preparation, your presentation. And again, this webinar will be posted and we'll send out links to the webinar and the scripts in the next day or two. So have a great day, everyone.
Thank you.